Hi everyone. We're gonna talk about solving the heat equation today. So let me list the content that I will try to cover um, as time permits. So first, I will try cover the part on solving the heat equation. Let's say the Cauchy problem. The heat PDE. So the problem is of the form, let's say the Cauchy problem that we have ut equals to Laplacian of u in Rn cross 0 infinity. And we are given the initial condition ux 0 equals to g of x on Rn. We will use a fundamental solution to solve this. And then there's the second point that I want to cover for today, and more if time permits. Second point is that I want to, uh, connecting the heat kernel to the fundamental solution of the Laplace equation in dimension 3 or higher. And then I want to um, um, also connect the Cauchy problem of the heat PDE um, with um, the Poisson equation for the Laplace PD over the Poisson. Okay, those are the two main goals for today. I will try to cover more if we have more time. Okay, so let's start. I want first to have a quick review on the fundamental solution of the um, so let's first just a quick recap. Quick recap on the fundamental solution of the heat equation. And of course, this is called the heat kernel, right? Short name for it would be the heat kernel. Let me recall its definition and then draw some of the pictures. We define phi of xt to be 1 over 4 pi t to the power n over 2 e to the minus x squared over 40 for x in Rn and for t greater than 0 and 0 otherwise. So let's say x in Rn and t less than 0. Okay. We have shown that the properties the fundamental solution that we have shown was that we show that the okay, let me go up here. The integral in Rn of phi xt dx equals to 1 for t greater than 0. So it's a Gaussian, right? I'll draw some pictures, but let me write things down first. And then we see also that phi decays exponentially fast as x tends to infinity. And further that we have a maximum of phi xt for x in Rn occurs when x equal to 0, right? The exponential is 1, which gives you the value that is equals to 1 over 4 pi t to the power n over 2. And of course, this goes to infinity as t goes to 0, polynomially. Okay, because we have 1 over t to the power n over 2 there, so it goes to infinity as t goes to 0. And schematically, the graphs of phi looks like this. This is x. This is, let's say, phi xt. Let me try to draw the graph as for different time. You can see that when t gets really large, the phi 0t goes to 0, right? So if t is large, then it's kind of like phi uh, is something like this. So let's say this is phi of x, let's say 10. However, when t gets smaller and smaller, uh, the function is when t gets smaller, oops, the function is putting more mass near 0. So let's say this is phi of x1, and say that as it gets smaller, I have more and more mass being concentrated at 0. This is phi of x, let's say 1 over 5, and so on and so forth. Okay. Uh, you know, gradually you can see that we put all of the mass near 0 gradually. Okay. So this really tells us that I mean the intuition is that as noted, right, phi x dt itself is a probability measure, right? And um, as t goes to 0, right, plus all of the, it's a probability measure because simply that the integral equals 1. So at t goes to 0, you can see that phi x t dx converges, I mean, weakly in terms of measures, but we are not talking about measure theory in this class, so it's okay. Weakly in terms of measure to the Dirac delta at 0. So it pushes all of the mass um, to just 0. Okay. So then that's the intuition, and you can see that in the literature people do write that phi satisfy the equation that I have phi t minus Laplacian of phi equal to 0 in Rn cross 0 infinity, and phi of x0 equals to the Dirac delta at 0. That you can also see people wrote in the literature. Um, this is more of a formal way. It gives you the intuition of how to handle the problem. Okay, so now let's go back to the so now let's go to the Cauchy problem, right? And that what I mentioned that we want to do for today. Cauchy problem. Let me write down first. How do we derive a formula, right, for the Cauchy problem, and then we will prove it rigorously. Let me recall again. The Cauchy problem is that I have ut equals to Laplacian of u in Rn cross the infinity, and g x0 equals to g of x, the given initial data. Okay, so here in our setting, say that g um, is a given bounded and continuous function on Rn. Okay, so it's bounded and continuous. Notationally, you can say that G is in BC of Rn. B stands for bounded and C stands for continuous. Okay. So what is the heuristic, right? I want to explain to you what's the heuristic of how we solve this equation. We use exactly, the heat equation is a linear equation, so we use the superposition principle, right? That we would like to add things together, um, because it's linear, so things can be added up, and so add things together. Specifically, how do we add things together? We're gonna use the fundamental solutions, and we're gonna use this identity. So this is heuristics, but it's a good guiding principle that g of x is nothing but the integral Rn of g of x minus y delta 0 y dy. Again, this is wrong because delta 0 is not a function, it's a probability measure, but you can see that delta 0 puts of its mass at y equal to 0. So you can see that only when y equal to 0 this is valid, right? So when y equal to 0 this is uh, g of x minus y is g of x. That's why you see that we put all of them mass at 0. And because of this, right, that suggests us that we can, because of the superposition principle, we can combine exactly the fundamental solution together to arrive at a solution. So this suggests us that we should have uxt equals to integral Rn phi of x minus yt. Uh, uh, what did I want to say? Okay. Yeah. So the above formula also equals to integral Rn. Um, delta 0 of x minus y g of y dy. I just want to switch the order so that it fits with this. Okay, so delta of x minus y correspond to phi of x minus y t, right? Because that's a fundamental solution corresponding to that. Multiply g of y dy. Okay, so that's a heuristic. And in fact, this is exactly our first theorem for the day. So let me state theorem number one. Uh, okay, we define for xt because the fundamental solution it's essentially only define for t greater than 0. So I define for xt in Rn close 0 infinity that we let uxt equals to integral Rn v of x minus yt g of y dy. Okay. Um, and of course, we have talked about convolution. This is nothing but the convolution of phi, the fundamental solution, or the Gaussian or a Gaussian, convoluted with g, computed at xt. Okay, so we define phi to be like that. Then we have the following. The first thing we have is that automatically u is in C infinity Rn cross 0 infinity for any positive term. Okay. The second thing we have is that u solves the Cauchy problem, right? So let me be specific. Ut minus Laplacian of u equals to 0 in Rn cross 0 infinity. And the third thing is that, well, you see that in this definition, we only define u for positive term because the fundamental solution is only defined for positive term. But the initial condition holds in the sense that I have limit at xt goes to x naught 0 of uxt equals to g of x naught. Okay, for x naught in Rn. So here what it means. This is time equal to 0. Let's say I pick this point x naught 0. What it means is that if I have a sequence of point xt Okay, metro. It's going to x naught 0, then the value of uxt will be equals to the value of the initial condition g of x naught. I'll explain in the proof, but this is inherently coming from the fact that the fundamental solution is squeezed into a Dirac delta, and hence um, push all of the mass to a point near x0, and as xt goes to x0, we have that the last class. Okay, right, good. All right, so now let's write out the proof of our theorem proof. Okay. The first thing that U is smooth is quite natural because this is a convolution idea, right? I mean, because U is phi convoluted with G and phi is smooth. This is already discussed in class on this. So let me prove one and two. One and two actually are quite easy to prove. Let me prove one quickly first. Okay, I keep the formula here. Um, see, you can see. Okay. Yeah, you can see the formula. Okay, so I have what? I have so I note that phi is smooth, right? Smooth in Rn cross 0 infinity, and I can differentiate it as many times as I like. And again, let me write down the formula so that we are on this, on the same page. Keep writing the formula. Everything gets more and more familiar. So we have this. And I recall that x only appears here and here, right? I mean, g, we are not going to differentiate with respect to g. So it's okay, right? So for example, and also t appears here and here, only in the fundamental solution, right? So we can differentiate u in x and t as many times as we want, right? Okay, maybe let me write down some examples. For example, we differentiate uxi of xt. This is equals to del over del xi of this integral. And again, g is continuous bounded. This integral is well defined. Phi is smooth, has mass 1, so it's okay. I can put the derivative inside, and remember that x only appears in phi, so clearly this equals to integral in Rn of phi xi x minus yt gy dy. Okay, and similarly, if I differentiate uxi xj xt, this, I differentiate once more in xj, the del over del xj come in, so it becomes exactly phi xi xj x minus yt gy dy, and I can differentiate more with respect to the x variable as many times as I want. And similarly, I can differentiate in t, right? So I have ut of xt equals to del over del t of this integral. And again, I can put the derivative inside, and t only also just appears on phi, on the fundamental solution. So that equals integral Rn phi t of x minus yt gy dy, and I can also differentiate as many times as I want on the t variables. Okay, so more derivative in x as many times as we want. Same for t. Okay, so at the end of the day, we conclude that u is in C infinity of Rn cross zero infinity. So this is a very beautiful smoothing effect of the heat equation. You just start with initial data that is just a continuous functions, but because of the convolution idea that as time goes, you automatically have that the solution is smooth in time. It's a beautiful property of the heat equation. And it's natural because you can imagine that if you start with sort of some rough differences in the temperature, what it does is that, the heat or the temperature get changed, right? I mean, get redistributed in such a way that hotter area, higher temperature gonna give some to the places with lower temperature. So it's kind of smooth things out, right? Because you know, it's get more harmonious as time goes. Okay. So they had that. So that's the first thing. All right. So now let me prove the second thing, which is clear because of the fact that the fundamental solution solves the heat equation for positive time. Again, um, we are not talking about time zero yet, right? But for positive time, fundamental solution solve the heat equation. Okay. So let's take any x and t in Rn cross zero infinity. What I have is that ut, okay, let me write out the variable clearly, minus Laplacian of u of xt. This equals the integral on Rn Vt x minus yt dy minus integral on Rn Laplacian of phi x minus yt dy. And the two integrals can be combined together naturally. That equals the integral on Rn pt x minus yt minus Laplacian phi x minus yt dy. And again, this is equal to 0 because for positive time, P is totally smooth and it solves the heat equation, and this equals to 0. Okay, so you see that this is a little bit different from the Poisson equation, because for the Poisson equation, there's a singularity in Rn, right, in the domain. So when we prove that the convolution of the fundamental solution with f solve the Poisson equation, we have to cut out the singularity and do it carefully. Here for the heat equation is different because the singularity appears in step 3 only, right? Because let me explain here in this picture, right? You can see that here I have, oops, um, here I have, so for the fundamental solution, oops, this is x, this is t. For the fundamental solution, I have phi t minus Laplacian of phi equal to 0, all up here. So for t positive, it's fine. There's a singularity, but singularity only happen at 0, right? Um, so I know that phi is singular um, as t goes to 0, right? And you can see that as we said, um, we kind of see that heuristically we have that phi of x0 equals to the Dirac delta at 0, right? So this is heuristically. Um, um, so the part that we need to be careful and we need to handle well is actually the last step here, the third claim, because we need to make sure that the when we define u, right, you can see that when we define u here, we only define it for xt in Rn cross 0 infinity, with 0 excluded because phi is not defined 0, and still we want to claim that as t go to 0, we go to the initial data g, and this is why it's delicate in this last step but not the middle step. Okay, so that's the thing we need to note. So we want to show what we want to show, that the limit at xt goes to x0 0 of uxt equals to g of x0. Okay. Um, for this step, we will use the idea that, again, as time goes to zero, phi is more concentrated and it goes naturally to Dirac delta by pushing all its mass at just one point, right? So how do we do it? Okay, let's write down epsilon delta proof. I mean it, but it's quite natural, right? Because we know that. So note that G is continuous, right? Uh, it's continuous everywhere, and in particular, it's continuous at x naught. So for epsilon greater than zero, there exists a delta greater than zero, such that you can also write this one in terms of modulus of continuity. Doesn't matter. Such that I have g of what? G of y minus g of x naught is less than epsilon for y minus x naught less than delta. Okay, so this picture. This is y. Oh no, x naught. And this is the radius delta. So for y within here, then gy is close to g of x naught. Okay, so that's that. Now I'm gonna take x closer to x naught. I mean, it's just a matter of technicality. Drop head ball. Uh, Now I'm taking just the radius delta over 2, and I'm gonna pick x closer to x naught so that I have better control. Okay, just from here to here, I have some better control. Okay, so take um, x closer to x naught. So in the ball of center x naught, radius delta over 2. Okay, and now I want to evaluate the difference, right? We compute. Okay, let me leave some space here. What's the difference between uxt minus g of x naught, right? This again, I mean, equals to uxt is given to us as a convolution of the fundamental solution with the initial data and subtract the initial data itself. Okay, and now I'm using the trick, and this is exactly the trick that we have used many times, that we multiply g of x naught with 1 because it's just g of x naught, right? um, but what is important is that what is 1? So, let me write like this: g of x naught, I multiply it with 1. This is 1, because remember that phi has mass 1, right? So this is 1. So we are just doing the boring trick of multiplying g of x naught with 1. It doesn't change the value, but the fact is that 1 is exactly the mass, or the yeah, total mass of phi, right? And this allows us to have a common term here, right? I mean, this one and that one are common, so and we can group them together. So this equals, let's group them together first. Integral Rn phi of x minus yt g of y, and remember g of x naught is a constant with respect to y, so I can put it inside the integral dy. Okay. And now I'm using the same philosophy or same trick like what we did for the for the Poisson equation, because we know that phi blows up as time goes to zero, and it blows up near the point when y equals to x, right? So I have to split it into two pieces. And here a good piece would be inside this ball of x naught radius delta over 2. Um, why? Because or radius delta, because inside this ball, yeah, okay, maybe let me highlight the whole ball. Inside this whole ball, that I have good control, okay? And then outside, I know that phi decays exponentially fast. So that's the idea. Okay, let me write down. Okay, so let me write. Okay, so this is less than equals to. I'm gonna put the absolute value inside, and then I break it into two pieces. The ball at center x naught radius delta, phi of x minus y t, gy minus gx naught dy. Uh, and then the other piece is where we are outside of this small ball, phi of x minus yt, gy minus g of x naught dy. Okay, as usual, I'm gonna call this one to be I plus j. So the first term is I, second term is j. Okay, let me explain intuitively wait, what? Let me explain intuitively that I is easy to be controlled. Well, remember that because y is within the delta distance close to x, so we know that from the above fact. Let me put a box up there. From the above fact, we know this is less than epsilon, right? And then the integral phi is 1, at most 1. So the first term is bounded by epsilon. The second term is that we are using a different fact. We are using the fact that phi concentrates of its mass near the point where y is close to x. So outside, it decays exponentially. So most of the mass is already inside, right? So outside of a ball is essentially gonna get to zero, and that's the idea. That's the idea to for the proof. Okay, so let me write down what I just said. Okay, so for one, so we control one first, right? Control one, that I have one equals. Let me just write down integral in this ball. And again, because this is less than epsilon, so I is less than integral on this ball, phi of x minus yt epsilon dy. And epsilon is a constant I put out. And this is less than epsilon times the integral. I'm going to use the integral on the whole space, right? Because this ball is just part of the space. So this is just put the integral on the whole space. And this equals to epsilon. So you see that the first term is already less than epsilon, and it will go to zero when we let epsilon go to zero. And then next, um, we're gonna control uh, uh, the second term j. Uh, we handle j, right? So to handle j, let's note a little bit. I drew the picture up there, but maybe let me draw it again so that it's clearer for us. So yeah, make it bigger. We have this is x naught, and I have two balls. This is radius delta over 2. This is radius delta, and I have um, x is within this ball, right? And now because y is outside of the other ball, y is here, right? So you can see that the distance from x to y is at most delta over 2, right? It's at most this distance, which is at most delta over 2. Okay, so let me write down. For x is in this ball, b of x naught delta over 2, and y outside Rn takes away this ball. What do we have? We have x minus x naught is less than delta over 2, and y minus x naught is greater than delta. So as a result, by the triangle inequality, what I have is that I should have x minus y. Uh, let's see. X minus y is gonna be greater than equals to y minus x naught minus x naught, right? This is equivalent to the fact that you have x minus y. Okay. Okay, plus x minus x naught is greater than equals to y minus x naught. That's the triangle inequality. So this gives you the fact that x minus y is greater than equals to delta over 2. Okay, so the distance is big enough. It's bigger than a fixed number, delta over 2. Okay, so that suggests me that I have j equals to this integral on Rn takes away b of x naught delta phi of x minus yt g of y minus g of x naught dy. Okay, so I'm gonna replace because we just proved that x minus y is greater than delta over 2, right? So this is less than equals to exactly the integral where I have um what? Where I have let me try to um uh, okay, where I have y, okay, y minus, okay, uh what's the best way to say it? No, it doesn't matter. Okay, I'm just gonna say that for y minus x is greater than equals to delta over 2, right? Of phi of x minus y t. And remember that I have g is given to be bounded, right? So g is given to be a bounded function. H of this is bounded by a constant c. So the difference is at most 2c times 2c dy. Okay. Um, and you can do a change of variable to make this nicer. This is 2c times the integral. Let let me change y minus x just to gonna be y. So I have integral of y greater than equals to delta over 2 phi of yt dy. Okay. So let me draw a picture here. This is exactly the intuition I was talking about. That this is y, this is phi of yt, and we fixed delta over 2 minus delta over 2 here. As time gets smaller and smaller, we are sort of pushing more and more weight to not good. We are pushing more and more weight to the inside, and as a result, the part outside that I'm sort of crossing out here, this part outside corresponding to this integral, it will get to 0 because it's exponential decay, right? How do you see that? I mean, you can even write this one converge to 0 as delta goes to 0. That's one thing. Or you can use exactly the change of variable formula, the formula of pulling things into this domain into balls. So let me write down. You can also write this one as 2c times the integral from delta over 2 to infinity the integral on h of the sphere. Uh, um, 1 over 4 pi t power n over 2 e to the minus y square over 4t ds and then dr, right? That's a formula. This equals to 2c, the integral from delta over 2 to infinity. Um, remember that we are on the sphere, so y square equals to r square. And the area of the sphere is n omega n r to the n minus 1 over 4 pi t n over 2 e to the minus r square over 4t dr. Okay, that's the integral you have. Um, you can pull all of the constant n omega n and other things out. So this is less than equals to c times the integral from delta over 2 to infinity. What do you have? You have um, r to the n minus 1 over t to the power n over 2 e to the minus r square over 4t dr. And you can see that this converges to 0 as t goes to 0. Okay, this converts to 0 as t goes to 0 because this goes to 0 exponentially fast, right? And this was also sorry, up here I wrote it wrong, not at delta goes to 0. Up here it should be as t goes to 0. Okay, this is exactly related to one of the homework problem that you were given. um, so it's very clear, and you can see that exactly what it says is the tail of the Gaussian is decaying very fast to 0, and it has to be 0, and all the mass is concentrated elsewhere inside here, right? So the mass concentration is being pushed further and further near 0. Okay, yeah. So hence what do we have? Hence we have that. Let me write down the conclusion here is that I have 0 is less than equals to I, less than equals to epsilon, and the limit as t goes to 0 plus of j is 0, right? So that's the conclusion. And that means that we should have limit as xt goes to x0, 0 of u xt minus g of x0. This limit has to be 0, right? Because again, epsilon will be led to 0, and let me recall here, you can see that we said that uxt minus g of x naught is less than equals to I plus j. J goes to 0 and I is less than equals to epsilon, and epsilon um, okay, maybe let me say uh, by by letting epsilon goes to 0. Okay, so that is the conclusion of our theorem, that we do have that again. Okay, maybe let me make a remark. Let me make some quick remark. And this is something quite beautiful, right? So the solution, you have uxt equals to integral on Rn phi of x minus yt gy dy, or you can write as phi convolute with g computed at xt. Again, g here only depends on y. That's why the convolution is only in the y variable. So there are a couple of points that I want to highlight here. Maybe 2 points is enough. Is that even though g is just continuous and bounded, we see that that uxt is smooth right away for t greater than 0, right? So this is the so-called the smoothing effect. Smoothing effect of the heat PDE. I already explained it. Let me recall very quickly that you can view this in two ways. The first way is because we are doing convolution with a heat kernel, which is smooth, and hence, convolution basically smooth up your function, right? That's a technical way to view it. Or the other way to view it is by physical interpretation, where you have that, for the heat type equation, essentially that the place with higher temperature gonna distribute some of the heat for the place with lower temperatures to even things out. And hence, in this process of evening things out, it's make things less rough, right? It can be first can be highly different, but then because this one is gonna give some heat to this one, so eventually it's gonna make things sort of smoother and smoother and smoother. That's the first thing. The second thing I want to say is that there's this so-called, besides the smoothing effect, there's the property called um, infinite speed of propagation. Okay, so what's infinite speed of propagation? Infinite speed of propagation here means that although that you can start with, so say, even if the initial data has compact support. Okay, there's some examples clearly in my textbook. So you can have a look. But let me, in this case, let me just draw a picture. So say that this is x, this is g of x, your initial data. Let's say that initially I have some heat distribution like this. So it has compact support. G is totally zero outside of a set of a ball. Um, so the temperature is positive here, right? But right after you run the heat equation, you can imagine that, okay, this is very hard to draw, but this is x, this is u of xt. You can imagine that because you do u equals to phi convolute with g, right? And okay, maybe you can write down this is u xt is, I'm writing this down so many times. Phi of x minus yt gy dy. Of course, you see because g is positive in a set, right? And phi is always positive. So you can see that uxt is always positive for all xt. Okay. So what it does is that although that the temperature at infinity is going to be very small anyway, but it does get some of the heat from this g, and then inside here is going to even things out, that the difference is going to be smaller and smaller. um, yeah, so you see that again, this one I'm not good at drawing, but you see that here the starting point could be that the difference in temperature could be higher, but as time goes, things gonna be even out. And if you go further, it's gonna get to, maybe this, even out more, and then it will go more and more. Okay. So those are um two very, very important properties of the heat equation, that they have the smoothing effect and the infinite speed of propagation. Infinite speed here means that right away, the temperature got risen to be non-zero everywhere. However, it's okay because although, maybe let me say, although um no, what Although u greater than 0 everywhere, we still have that uxt actually decays, goes to 0 exponentially as x goes to infinity. So physically, it's physically relevant and fine. The fact is that far, far away, roughly speaking, in ideal situation where there's no frictions, no whatsoever, then you do send some of the heat to infinity, to faraway places, but in principle that cannot be felt because it's exponentially small, right? So that is in an ideal situation. In real life, when you have frictions, when you have all this um, sort of parameters and all these situations, that doesn't allow for the heat to get infinite propagation too far away, then it's also very natural, very physical. Okay, so that's that. All right, so now let me go to the second part that I want to explain. I already explained this a bit in the lecture, but let me go in systematical way. Okay, so let me say a relation between the heat kernel and the fundamental solution to the wait what to the Laplace PD. And this I can only do it in dimension n greater equals to 3. Um, so let me state the theorem and explain to you the proof first, and then I'll give you some intuition and an application. This is really cool, because essentially you have the heat equation that has time. How do you want to get rid of time? You integrate with respect to time, and that's the point. When we integrate the heat kernel with respect to time, we get back the fundamental solution of the Laplace PD. Okay, so let me write down the theorem. Theorem 2 for today. Assume n is greater or equals to 3. Then we have, for x not equal to 0, the integral on Rn, not Rn, wrong. Integral from 0 to infinity of the heat kernel dt. Okay, let me write down. The heat kernel has a formula, right? 1 over 4 pi 4 pi t to the power n over 2 e to the minus x squared over 4t dt. I'm integrating with respect to time. This will equal to uh, the fundamental solution of the Laplace equation phi of x, which is 1 over n times n minus 2 omega n, which is the volume of the unit ball in n dimension, times x to the power 2 minus n. Okay, so this is to me a very cool result. Um, the proof is simple, just by change of variable. Well, given that we accept some of the facts on gamma functions, because we surely gonna accept some of the facts with the proofs, yeah, just computations. The key point is to see this through a change of variable. Okay, well, I have this exponential here, right? So I want to do a change of variable to make it simple. The change of variable is simply by let s equals to x squared over 40, so that I have, it's the integral of e to the minus s, just that. Okay, and in this case, I would have ds equals to x squared minus x squared over 40 squared dt, just that. Okay, so what does that mean? I mean, let me write out two things here, because I did this in class last time, but it was in a hurry. So that means that um, I should have what? I should have dt uh, equals to minus 40 square over x square ds. That's what I have. And let's plug it in, right? And then we see more. Okay, so let's plug it in. I would have integral from 0 to infinity p of xt dt equals um when t is 0, then s is infinity, and when t is infinity, then s is 0. So infinity to 0, um 1 over 4 pi t to the power n over 2 e to the minus s minus 4t square over x square ds. Okay, and because of the minus signs, I can switch the integral to be integral from 0 to infinity, right? Okay, I have t here. Let me be careful. Okay. Yeah. Okay. So I'm gonna write this in terms of s because I have. Let me split the pi out. So this is equals to 1 over pi to the power n over 2 times. Let me write like this. 1 over pi to the power n over 2 times 1 over 40 to the power n over 2. Okay. Um, times I want to cancel things out. Okay, let me just write like that. E to the minus s 40 square over x square ds. Okay. Again, for this kind of terms, this term and 40 square, I'm gonna still change it to s, right? Because I have to change a variable to s. So I want to be careful here by changing all of the variable to s. Okay. Um, so what do I have? Wait, there's something. Give me 1 second. Yeah, but okay, fine. So this equals to uh, I I take this one out, 1 over pi to the power n over 2, integral from 0 to infinity. The first term is nothing but just s to the power n over 2, right? Over x square to the power n over 2, because you can see that 1 over 40 is exactly s over x square, okay, times e to the minus s times 40 square. I still need to write down 40 square in terms of s and x. So what do I have? I have t square is okay. What's the better way to say it? It's okay. So I have t square is x square over s square over x square ds. Yeah, sorry about this mess. It's just computations. So okay, now you can simplify everything. This equals to 1 over pi to the power n over 2. The key thing here is that we keep track with the term x. Let me highlight the x here. I have this is one x, this is one x, and this is one x. So I have x appears in many places. Okay, so let me see what are the x that I have. So this is nothing but times x. The first one is to the power minus n, and then I have to the power 4 over 2, which is 2. So I have it's exactly x to the power 2 minus n. That's exactly the key thing um, from the fundamental solution of the Laplace equation. That's the key, right? And then the rest is just integrals. Integral from 0 to infinity. What? Um, e to the minus s times s to the power uh, n over 2 minus 2. Okay, n over 2 minus 2 ds. And this is something called gamma function. Um, this is something called gamma function. I'll explain, but gamma of n minus 1 of n over 2 minus 1. Um, but anyway, it's a gamma functions. There's this formula for it. And we can say, let me just say it right away, that this equals to nothing but 1 over n times n minus 2 omega of n x to the power 2 minus n. Okay, so that's we are done. We are done by accepting some facts on gamma function. So let me write a remark on gamma function. So a remark quickly on gamma function is that uh, again I have the gamma function of n over 2 minus 1 equals to this integral. In case you are curious, you don't have to worry about this. I just want to explain if you are curious. So we have some properties of gamma functions. Functions that I have, well, function that I have gamma of n plus 1 over 2. I have a recursive formula. This would equals to n over 2 times gamma of n over 2 and equals to n over 2 times n over 2 minus 1 of gamma of n over 2 minus 1. Okay, it's just a recursive formula. And if we compute this is n times n minus 2 over 4 of gamma of n over 2 minus 1. Okay, so this gives us the fact that this gives us the fact that uh, this gives us the fact that 1 over pi to the n over 2 times gamma of n minus 2 n over 2 minus 1. This equals to um, I'm going to relate gamma of n over 2 minus 1 with gamma of n over 2 plus 1, right? Uh, by this relation, I see that this is equals to 4 over pi to the power n over 2 times n times, okay, n minus 2 times gamma of n over 2 plus 1. Okay, I have this relation. And as a matter of fact, what is known is that this is exactly 1 over n times n minus 2 omega n, where we use the fact that the volume of a unit ball in Rn is nothing but pi to the power n over 2 over 4 times gamma n over 2 plus 1. So that is a fact. Um, you know, just a constant. Okay. Um, so you can ignore about this technicalities of integrating in the gamma functions, but the key point is that I want to make is that when you integrate the heat kernel, you get back to the fundamental solution of the Laplace equation. And again, this works for n greater equals to 3. I don't want to get into the detail here, but I want to get to the point that I want to make. Is that then how do we connect the heat equation in connections to the Poisson equation, right? um okay, so again, the theorem 2 gives us the following. Theorem 2 gives us that for n greater equals to 3, I integrate the fundamental solution, the heat kernel, and I get back the fundamental solution of the Laplace equation. Okay, so as noted for the heat equation, right, I have ut minus Laplacian of u equal to 0. I have ux 0 equal to g of x, right? This is a Cauchy problem. Then I have the solution is this. Okay, and now I note the fact that, um, okay, maybe let me just say that as G is compactly supported, okay, okay, no, I should um, assume now that G is compactly supported and in C2 of Rn because I want to link it to the Poisson equation. Maybe let me write it minus Laplacian of V equals to G in Rn. So that's a Poisson equation I want to link to. I assume now G is like that. And because G is like that, you can see that we already say that um, as for the heat kernel, right? As t goes to infinity, the heat kernel is going to zero because the maximum point here of the heat kernel is 1 over 4 pi t to the power n over 2. This goes to zero as t goes to infinity. And because G is compactly supported, we can see that uxt converge to zero as t goes to infinity. This is natural because you just have some amount of heat. When it gets sort of diffuses everywhere, as time goes to infinity, it just diffuse so much to everywhere that is kind of essentially goes to zero everywhere. Okay. Now, I want to go from the Cauchy problem to the Poisson equation. And how do I do it? So this is the another heuristic, right? So it's a heuristic that, to get rid of time, well, we just integrate with respect to time, right? We integrate the time out so that time goes away. So that's the point. Let's write out the proof. Okay, so proved uh, that we can go from the heat equation to the Poisson equation. Well, I just need to define v of x equals to integral from 0 to infinity of u of xt dt, right? So I integrate with respect to time. Then what do I have, right? What I have is that, yeah, I can write out the formula, right? So because I know what is uxt, so integral from 0 to infinity, integral in Rn, phi of x minus yt gy dy dt, okay? And now I'm gonna use Fubini, right? Because I can change order of the integrals. This equals to integral in Rn, integral from 0 to infinity, um, phi of x minus yt d dt first, gy dy, right? Because the y is independent of t. And this gives me, by theorem 2, this gives me that this is exactly the fundamental solution to the Laplace equation, phi of x minus y gy dy. Or you can write as phi convolute with g at x, right? That's so. Okay, so it's really cool that when I integrate respect to time, I see that v is exactly the convolution of phi and g. Okay, and now I'm going to show that, so that's the first part. And second part is that we show that minus Laplacian of phi of x equal to g of x. Okay, remember earlier when we did this, we had to do use a technique of cutting out the singularities by a small ball and then let that ball goes to the radius of that ball goes to zero. So that's sort of the natural techniques from singular integrals, right? But now we can do it differently because we already proved that you solve the heat equation. Okay, so this is a different proof, right? By using the heat equation. How do we do it? Well, we just compute, right? So we have the formula for v, and we plug in minus Laplacian of v of x equals to minus Laplacian of this integral, uxt dt. And this is integral with respect to t, so we can put the Laplacian in anyway. So this is um, integral from 0 to infinity minus Laplacian of u of xt dt, and minus Laplacian of u is equals to minus ut, right? Because you solve the heat. Wait. Yes, minus ut because you solve the heat equation. So minus ut xt dt. And now we can compute, right? This equals to minus u xt, because it's just a fundamental theorem calculus evaluated at t equals to 0 and t equals to infinity, right? So as noted, as time goes to infinity, u goes to 0. So this equals to minus 0 minus uh what? Um okay. Minus of ux0. Okay. And we know that ux0 is exactly g of x, right? So this equals to g of x. Okay. So that gives us exactly another proof of the of the solution to the Poisson equation. This is to me very interesting because the key point that I want to make is that we can use heat kernel, right? Heat kernel uh, to get the fundamental solution to the Laplace equation by integrating with respect to time, and effectively that means also that we can uh, effectively that means that we can mm, use okay, we can use solution to the heat equation, the equation with time, to solve uh, um, to solve uh, Laplace equation. Okay. um, it's a very natural idea, and in fact that this idea is used a lot in other contexts. For example, I can tell you that in the context of random walk in random media, so just for fun, and to conclude our lecture is to say that this sort of principle is used a lot in modern research, right? Modern research. For more general things on parabolic PDE, and the hit kernel and hit kernels to go to elliptic PD and fundamental solution and uh, uh, yeah, green kernel, but just fundamental solution. Fun- Fundamental. Um, and for example, we use it in the context of discrete type PDEs from coming from random work in random media too. For example, there's some work by Sao Chin Guo at Cincinnati, who was a postdoc at Wisconsin, and myself, that we use it in the context of random walk in random environment and other things. So it's really useful in many places. Okay, so let me stop the lecture here. Next time we will work on so next time we will work on a heat equation on a quadrant. So we are just going to solve it in the first quadrant here. Um, and then maybe also we start moving to let me see. We will then start moving to Mach's principle. Okay, so we will do a heat equation on a quadrant in the first part, and then we move to Mach's principle in the second part. Okay, thank you. Let me stop.